Okay, so all right, so let me define the model that we are considering here. So unlike arithmetic circuits that we have been seeing for a while now, we will talk about Boolean circuits. So the model, just to remind what the model is, for each input length, so we are considering non-uniform model of Boolean circuits. So for each input length, there's a circuit C of n for n greater than or equal to 1. And C of n is just a directed acyclic graph. It has 2n special nodes called the input nodes. Okay, and each of this node is labeled with either an input variable xi or its negation. And then there's a special output node, which is so these nodes have in degree 0, and there's an output node with out degree 0, which outputs the value of the circuit. And at each internal node, we label each non-input node essentially with some Boolean function that comes from a basis set. So typically the basis set consists of simple Boolean functions like or, and, well, in our case as well, mod m, and so on, right? So we consider a fixed basis set, and then we label the input nodes with these functions, and the circuit naturally computes a Boolean function, right? So just to be sure that we understand what I mean by this is, so define the threshold k function, which is defined to be 1 if the sum of the input bits is greater than or equal to k, is 0 otherwise. So here is a depth 2 circuit for that. Oh, I think I draw circuits the other way as most people draw, because I mean in my case the circuits information flows from top to bottom.
Maybe they'll reverse the video cameras. So
okay, or I can. No, I can draw it this way as well. And so this is a simple circuit. This is the fan-in of the output gate, and this is n choose k. And as you can see, that this circuit does compute the threshold k function. So so clearly the depth of this circuit, which is the length of the longest path from the input nodes to the output node, is 2, and the size of the circuit is order n to the k. And for the purpose of this talk, in this talk, we will always assume that the depth of the circuit is a constant, meaning that it does not grow with the input length. Right? So in this case, it's depth 2. So now look at, if k was non-constant, if k is a constant, then this is a polynomial size circuit. It has size n to the k. And but if k is non-constant, then this strategy does not work. Right? This makes the circuit of super polynomial size, so you cannot compute efficiently in this way the threshold k function, right? But if you allow more depth, then you can do something better. I won't go into the details of that, but let me just quickly say that here's one way to be more clever. So let's go to depth 3. And now what we do is, so we're building a random circuit probabilistically. So these have fan in K, and you sort of what you do is you pick each variable. So each of these subcircuits is being constructed probabilistically. So how do we construct a depth 2 circuit probabilistically? Well, take an xi, and then treat them as buckets here, or colors, right? And randomly choose one of the k possible places to set to assign xi to. It's exactly the way that you were doing sort of yesterday.
Yeah, it's exactly a perfect hash.
It's exactly yeah.
So it exists also explicitly.
And it exists explicitly, exactly. So just by yesterday's calculation, you can see exactly that if you have k equals alpha log of n, then with this fanning about I don't know, n to the delta, where delta is greater than alpha, this will suffice to construct a circuit that counts threshold k, right? Again, for the same reason, because if there is a k tuple which witnesses that there are k bits being set to 1, one of these OR gates would fire, right? One of these AND gates would fire, one of these subcircuits, and therefore the circuit would output threshold k. So in any case, so if you have more depth, you have more power, right? And a famous result due to several people, I think Fagin, Klopp, Pippinger, Stockmeyer, then there is somebody in the middle that I forget, and then there is Ragde and Wigderson. In a series of works, they showed that actually you can be more clever, and you can do an explicit circuit that is of linear size and can compute threshold polylog. Okay, of course not in depth 3 with more depth. So if you have more depth, then you have more power, and
constant depth?
yeah, constant depth.
The
Yeah, exactly. Depends on the exponent of the polylog. So for this talk, I will always consider constant depth circuits. So whatever I say would mean constant depth circuits. Okay. So yeah. Now, so these circuits can do non-trivial computations. So I'm just reminding you what we know already. So a natural question is, how do we prove lower bounds for that? Meaning we have now we are considering constant depth circuits with just basis set being OR and so there's no MODm, right? And this is a famous result. Again, let me remind you. Okay, maybe okay. So let me define the class AC0 to be the class of functions that are computable by constant depth circuits in polynomial size. So constant depth, poly size, and just using AND gates, OR gates and AND gates. Right. So the lower bound that we're interested in is what function is not an AC0. This is now a celebrated result. Well, we can show that the parity function is not an AC0, right? Where by parity, I mean you just count the number of bits set to 1. If it's odd, you output 1. If it's even, you output 0, right? And this is a result due to several people: Aitai, First Saxon Sipser, Yao, Astad. I mean, the bounds were Hastad eventually got the optimal bound, so the bounds improved with this series of works, right? And so how do they prove this bound? So the basic thing is, the basic intuition is, well, what is the weakness of an individual gate in this circuit? Well, an AND gate is fixed by restricting one of the input variables to 0, right? Then the AND gate gets fixed to 0 no matter what you assign to the other input bits. And the OR, likewise, if you fix one of the variables to 1, then the OR gate gets fixed. Now, in constant depth, a remarkable thing happens when you have these basis functions, that this weakness of the individual gates somehow propagate to the whole circuit, meaning, so this is the intuition. This intuition would be important for us, is that in constant depth, weakness of individual gates give rise to the weakness of the circuit. Right. So let's make this formal, because this can be formalized for AC0. So what they proved essentially is the following. So I'm stating the result due to the optimal result almost due to Hastad, which says that there exists a restriction to the input variables leaving n over log of s order d variables free, where s is the size of the circuit, right, such that the circuit, so there exists a restriction, let's say rho, such that the circuits, such that the restricted circuit, C of rho is the restricted circuit, gets computes a constant function over the free variables. Right? So that's the theorem. Now, this is very strong, because this says that no matter what your circuit was, if the size is s, then you only need to, so you have still a lot of, so let's say s is polynomial, for instance, then log of s is order log of n, and d here is the depth of the circuit, so you still have lots of variables free, right? And you have that many variables free, yet somehow the circuit gets fixed. So for instance, if you take a robust function like parity, which does not get fixed, even if you leave one variable unassigned, you cannot compute that, right? And in general, if you have the MODm function, so the MODm function would be, well, I will define it as simply a generalization of parity. Parity is mod 2. MODm is the Boolean function that outputs 1 if the number of input bits set to 1 is non-zero modulo m and is otherwise 0. Right? So in general, therefore, you cannot compute the MODm function. And so a natural question then is, okay, no, before I go to that, let me say, so what's at the heart of this this result? So how do you prove this result? Because that would be important in some of the results that we will see, is the following a lemma, which is called the switching lemma. So actually there were various switching lemmas devised by all these people, and I'll state a version which is very convenient to use in the presence of MODem gates, and this is due to Beam, Paul Beam. So Beam's switching lemma so this states, so if you have let C be a depth 2 circuit with bottom fanning R. So by bottom fanning I mean this is R, this is N, so the fanning of each of the gates at the base layer is R. So consider any such circuit with bottom fanning R, then if I choose, then if we choose a restriction at random from the space of okay, so by this I mean the set of all restrictions that leave exactly L variables free, and out of the original set of n input variables. So if I choose a random restriction from the space, then the restricted circuit with high probability, with probability, in fact at least I'll just say what this means. Not D. So P here is just so L is P times N, right? Okay. So with probability at least this much has a decision tree of height S.
That's really Rasborov switching lemma, which is explained very nicely in Beam's
Okay.
switching lemmas.
Right, this appears in the survey, so it's Rasborov's, okay. So
Rasborov variant of the Rasa switching lemma. That has a very different proof from us.
okay, so
S is the height of the decision tree or the size of the circuit?
no, S is the height of the decision tree. So maybe we should change it T or H. Let's say H is better. So L is P times. So it's sort of that it's not quite the same, because you're not restricting each variable independently at random, but they're almost independent, right? In particular, if L is very small compared to N, right? In order to understand why this is called a switching lemma, right, which is, notice that the following thing happens. So you have a circuit like that, and you're hitting it with a random restriction from this space, and then this says that the restricted circuit will have a decision tree of height at most h. Now, I guess everybody knows what a decision tree is, right? So let me assume that that people know what this. Yeah. So if you have a decision tree of height h, then you have the following advantage, right? So look at all the paths in the decision tree that lead you to a zero answer, right? And if you consider all such paths and do a disjunction of those paths, then you get a depth 2 circuit for the negation of the function, right? And now if you negate that again, so the effect of this is that you get a circuit of this type, right, from here to here. Okay, is that clear that this lemma implies this? Because you have a decision tree of height at most h, right? And that's what we are using, right? So that's why this is called a switching lemma, because you can switch an OR of ANDs into an AND of ORs. And imagine now you have a circuit of depth d. You hit this. So assume for the moment that the bottom fan-in is R, right? And now you can hit this circuit with a random restriction, and you can now, if the bottom two layers were ORs of ANDs, you get into AND of ORs. And now again, so I'm considering a layered circuit, so at depth 3 and depth 2, now you can merge them, and so this collapses the two layers, and the depth decreases from d to d minus 1, and you can keep doing this, right? So, the size.
You only count the part really above the current depth.
Yeah.
Since then the size doesn't change because you're leaving the top part of the circuit alone.
Yeah.
We're replacing the bottom levels, and we only really use the size of the top parts of the circuit.
Right. Right. So I mean, the way we just set these parameters, you will see that the size also does not increase much, because here is a specific way. So let me show you quickly how this leads to parity not being to the result that to this result, actually. So because we will sort of use this as a black box several times. So so what we do is we consider a series of restrictions, right? I mean, so let's start with so rho 1 to rho. Our big restriction rho will be a composition of these restrictions. Okay, and so first, it's better to think of them acting one after the other. So rho 1, what it does is, so let's say for rho 1 we define P1. So let's say 1 over 14, right? And so what it does is, at the bottommost layer, let's say you have OR gates, right? And so this you can think of a depth 2 circuit with bottom fan-in just 1, right? If you just consider a single OR gate, right? This is the same as having this, right? So if I set P1 equals 1 over 14, then, and if we plug it in here, so R is 1 because the bottom fan-in is 1 to start with. So I'm just showing the base case, right? Then you have the probability that this is not going to have a decision tree of height h. So let's say h is log of s, where s is the size of our circuit. Okay, so let's assign h to be log of s, where s is the size of the circuit. So then the probability that you won't have a decision tree of height h is, just plugging in there, is less than 1 over s, right? Because you have 1 over 14 times this, so it's 1 over 2 to the s. So that's 2 to the log of s. So that's just 1 over s, right? That rho, the probability that rho fails is 1 over s. And since we have just s many gates, there is a restriction that's going to work, right? So after the first restriction, we have now a decision tree of height log of s. Right? And then we are going to plug for each of them. We define rho I to be, or Pi to be, 1 over 14 log of s, for instance. Okay, and then since now we can assume that the bottom fan-in is always log of s, we can keep doing this. And at each layer, the probability that it fails, a particular subcircuit fails to have this decision tree of height log of s, will be 1 over s, and we have s many gates at a layer, right? So by the union bound, we always succeed. And once we compose this d minus 1 times, we've got a decision tree of height log of s that computes the output of the restricted circuit, and now you're done. So if you Well, first I set P1 equals 1 over 14 to handle the bottommost layer. Then I've got a decision tree of height log of s,
But generally P will be
1 over 14 log of s, right? And my r thereafter, sorry, not r, h thereafter would be log of, h stays to be log of s, right? So at each layer, I'm going to, for each subcircuit, I'm going to succeed with, fail with probability at most 1 over s, in fact, less than 1 over s, and I have s gates at any layer, right? So I keep succeeding. And so, the end result of this restriction is I have a decision tree of height log of s, and the number of free variables now. So at each point, you see I'm decreasing by, okay, maybe
14 log,
yeah, exactly. So at each point, I'm decreasing by So at each point, I decrease by 14 log s. So I have a decision tree of height log of s, and at each point, finally, and at each point, I'm decreasing by 14 log. Well, first I decrease by 14, and then 14 log of s raised to the d minus 1. Now this, so I have a decision tree of height log of s. So if I set these variables to something, then the circuit gets fixed, right? So this better be greater than or equal to the number of free variables that are remaining. Otherwise, I cannot compute a function like parity, right? And that gives the bound for, that I guess gives the bound for parity, which is something like this, right? Right. So that gives an
One if you want to be precise.
sorry.
There's d minus 1, which is very
No, I get
actually
yeah. I think it's.
The thing is, it could be a d minus 2 because you stop at depth 2.
That's right.
Right.
Oh yeah,
Yeah,
yeah.
d minus 2. And it's interesting just because it's complete. It's 2 there and 1 there. It's 2 up there.
Here.
Sorry, yeah.
Yeah, there. And then bring
you get
down the log s.
Yeah. Then of course I get a d minus 2 here.
1.
Oh yeah.
And this is completely tight up to the real constant in that one. But that's,
But then you didn't use the theorem as so you don't continue until it is a fixed circuit until it is
Yeah. One. I mean, I continue with one layer below.
because you cannot even do parity with on n over polylog n variables by decision tree of depth polygon. Yeah.
Right. Okay. So the upshot of this is that you get exponential lower bounds for using this method, and okay. So this is the heart of the argument. Now the trouble with this is if we have MODm gates in our circuit as well, it's a very natural question now to say what happens if we plug in MODm gates into our circuit. So we expand our basis set, we allow MODm gates. And then, of course, we can't use anymore the switching lemma because, you know, I mean, to fix a MODm gate, you have to almost fix every bit of every input bit, right? Otherwise, it doesn't get fixed, and so this argument fails. Okay, but well, I can erase this part now. But what function should we expect to be hard when we have MODm gates as, so now I define the class ACC0, which is again constant depth, polynomial size, and the basis set is, actually let me define ACC0M. Right, and ACC0 is nothing but the union of that. Right. So, so what function should we expect to be hard for ACC0 of M, let's say, when we have just MODm gates along with AND/OR gates? Well, let's look at that intuition again, right? I mean, it's tempting to go back to that intuition. Well, first, we should identify what's the weakness of a MODm gate. Right? We already know what is the weakness of AND and OR gates. So Okay, so the first weakness is that the output of a MODem gate does not correlate well
Maybe it's better if you write a little bigger for the.
Oh, okay.
It's okay, you can just continue.
It's not efficient. So ACC0 is you allow all gates with any M.
Yeah, but fixed M.
The same, but isn't it the same as allowing? Because you can take any thing with many different M's and use a single M that works for all of them.
Right, right.
That's the reason why you define
You can.
Yeah.
Okay.
Yeah.
I mean, the standard definition usually allows even in the
Different.
buckets M1 and M2 and.
But you can always make it into one M, right?
You take the product.
I mean, you take the LCM of all of these, and then
It's doable in.
since each of these M1, M2 are fixed, the LCM is also some fixed modulus, and so you find it somewhere, right? Okay, so so the output of a MODem gate does not correlate well with a mod Q function, right? This can be formalized, right? I mean, we can formally say that, but sorry?
For Q that does not.
Yeah, sorry, yeah. So, well, if M and Q are relatively prime, right? So that's one weakness. The second weakness is if you consider the support set of a MODem gate. By support set, I mean the number of points in the cube where the MODem gate is non-zero, right? That's very large. Well, unless the MODem gate is a trivial one, which I'm not considering. So support set of a MODem gate is large.
Only 1 over M fraction. Or
Yeah,
something.
it's compare it to the O, or N, where the support set is exponentially small. Right? There's only 1 point.
That's a weakness or that's a strength?
Well, okay, that's a.
Well, I'm going to think of it as a weakness because I will consider functions which have low support.
Yeah,
right?
I think
I mean, this is a feature. You're right. This is a feature, but I'm viewing it as a weak.
Support, you mean the things that are not 0 modulo M.
Yeah,
So it's 1 minus 1 over M.
yeah.
And
That fraction, right, of 2 to the n.
fraction, yes, so it's
It's a constant fraction.
It's a constant fraction. So, but if I have the and function, for instance, it's not a constant. It's 1 over 2 to the n fraction, right?
well, the comparison will be the not of the end.
You want, when it says the support is large, you want it large, both this and the complement.
Yes.
So that's not true for N or Russell wants to say.
So somehow, if you want to prove a lower, I know you're working to a lower bound on just MODem gates without the and or.
Right.
If you want a real lower bound on ACC, you somehow have to combine the weakness
Of the and.
of the and or and mod.
Right.
It has to be somehow generalizable to a common weakness.
Right, but this will be so my point is this will be an intermediate step because we don't know of any lower bounds when we just have MODem gates, right?
Yeah, but you didn't say that you were going to focus on only
Oh, okay.
modern gates. That's what Russell's comment.
Okay.
Yeah, we don't. At this point, we are just looking for features we can utilize in any argument to prove something.
Right, right. Yeah, so this probably I should call it as weakness or features. I mean, we will try to turn these features into weakness of the MODem gate in our argument. Okay, so now again having the same intuition in constant depth, so it's tempting to conjecture the following things. So the first is a famous conjecture due to Smolensky. Which says that the mod Q function cannot be computed by ACC0 of M for MQ co-prime. right? In fact, his conjecture, I think he made the stronger conjecture that this cannot be computed in sub-exponential size by such circuits. Okay.
Is any non-trivial algorithm known?
No. So that's a good question. So
There are low bounds, right? So that's the 3 with mod M gates with mod Q gates to compute mod M.
well, if m is 6, there are no lower bounds known.
No, for primes.
Yeah, for primes, for any arbitrary constant. This is what Smolensky proved. But I'm not considering general M. I'm not considering M to be prime or prime power.
So there's a big difference.
Yeah, I was going to get there. Okay, so yeah, so the general conjecture is this, right? I mean, no matter as long as M is fixed, no matter whether it's prime or not, if M and Q are co-prime, then this mod Q is hard, inherently hard for such circuits. And in fact, this is polynomial size, but the conjecture is a very strong one. It says that even in sub-exponential size, you cannot compute this, right? So that's
Immediately implies an explicit function out of this.
right, because this would mean that, for instance, majority cannot be computed. Is that what you were saying?
I was thinking of the simple one that gets Q as an input, but
Q as an input?
Well, Q is any fixed number, so that is an explicit function.
Yeah.
No, but there is no
I thought by explicit you meant for ACC 0, this would give majority is not there, right?
Right.
Right. So that's what I was saying, right? Because for each M, there is mod Q that you cannot compute. And if you could compute majority, you could compute any mod Q, right? So this would imply that majority is not computable by sub-exponential sized ACC 0 circuits, right? Okay. So this would implies that this implies okay, well, that's the conjecture, but the progress is very bad. I mean, the progress is even if you have, I think if you have more than log square n mod m gates, even mod 6 gates, well, we have no lower bounds, no non-trivial lower bounds.
Okay, probably the most significant is what you mentioned, but you didn't. So it just affects it for primes.
Yeah, why don't you write down the
Oh,
result of
oh,
primes,
okay.
just in case there's no-
Okay, yeah. So for theorem, for any m which is a prime power, right? P is a prime. And k is a fixed number. Okay, so that's the theorem of Razborov and Smolensky. And so each of these, I mean, this is true, so therefore that is true.
How do you compute mod Q as majority?
Actually, you can compute every symmetric function with majority because you can count, right? So in depth 2, in fact, you can do that. Well, I mean, you just
spend the factor of n even, right? Padding with ones the input and then all the counts.
yeah,
Get all the counts, so
Right.
you know exactly how many ones.
Yeah.
there is.
you can do any symmetric function. With a little trick, I mean, you can do in linear size depth 2 even. Okay, so right. So for general M, as I was saying, that even we cannot handle omega log square of n many mod 6 gates. That's a recent result. I mean, log square of n gates can be handled. That's a recent result of Hansen. I'll get to that later. So if you have logs, let me state it just. If you have log square n many mod 6 gates or any mod m gates, then he cannot show the strong form of Smolensky's conjecture, but he's able to show that you need super polynomial size. So strong form of Smolensky's conjecture says you need exponential size. He gives you a super polynomial lower bound for such circuits. When you have log square, roughly log square of n many MODm gates. The other conjecture is, and this is why I wrote this feature. A natural class of circuits is when you have just MODm gates, right? And this is also a universal class. So it's interesting to see that if you just have MODm gates and and OR gates or AND gates, that's a universal basis already. That can compute every function if you don't restrict the size. In fact, it can compute in depth too.
So now M is never a prime.
If M is not a prime, then it is true that it can compute every function. So let me define the following class. So we call this CC0 of M, which is constant depth, polynomial size, and the basis is just mod of M. Okay, and CC0, just as like ACC0, is going to be the union of M. Okay.
So you're not going to talk about the proof of Arkadev-Chattopadhyay. You will not.
No.
Yeah. So let me just mention apropos something that Boaz asked before. Boaz asked if there are non-trivial upper bounds. So the way that Arkadev-Chattopadhyay lower bound works is by approximating these circuits, which have AND, OR, and prime gates, approximating them by polynomials. And
Oh, this I was going to talk about. Okay, just outlining.
I'll just okay.
Yeah.
So I'll just mention one non-trivial thing. The AND function, when you represent it as a polynomial modulo prime, always has degree n. Okay, so the O or n function. But a non-trivial upper bound of Rudish, Beagle, and you were going to.
Yeah, I was going to talk about that. Barrington, Beagle, Rudish.
Yeah. So there are non-trivial upper bounds. For example, mod 6. When you represent the O, you can write it as a polynomial of degree root n. And
It's not
mod
known.
15, you can do it in cube root of n. And if you have t primes, you can write it as the
Tth root of n.
And it's not known if you cannot even do it in log n.
Right, exactly. So I was going to get into polynomial representation because I'm going to need them anyway. Okay. All right. So yeah. Where are we? So let me just briefly mention the conjecture that we have for this. So I mean, a good question is obviously, what can MODm gates do? I mean, we don't know of any non-trivial computation using MODm gates. So it's not clear why this is hard. Why going from primes to a non-prime? Is it just a technical difficulty, or there are good reasons? Meaning, I mean, I just showed you that in depth 3, and an OR gates can do some clever computation, right? I mean, they can do threshold log of n. Nothing of similar flavor is known if we have just MODm gates. The only function that you can think of is MODm or some variant of it. But no algorithm, no circuit is known that's non-trivial.
Will you show that it's universal? So even just the fact that it's universal?
Yeah, I can show that. Okay, yeah. No, I'll probably not show because I'll run. Yeah, it's an exercise. Yeah, I'll probably leave that. That in depth 2, if you have mod 6 gates, you can compute every function in exponential size. But I probably wouldn't have time. Yeah.
Probably if you don't care about the depth, is not how to show that you can do OR and of 2 bits.
Sorry?
Probably it's not how to show that
Yeah,
you can do end of 2 bits
yeah,
using this thing.
Yeah.
If you
It's not closed.
if you can count mod anything bigger than 2, then you can express that the sum of the inputs is
Right.
exactly 2,
Yeah.
and that's the end.
Yeah, but that will just show you for constant bits. But if you want to show that in depth 2, you can compute everything, you have to be more clever.
That wasn't what he asked.
Okay, so the conjecture here, and this I call the small support set, or actually I should call a large support set, depending on what, is that if C is of size S and comprises only MODm gates, then
Do you want constant depth? No?
oh yeah, I'm assuming always constant depth. Sorry, yeah, C is of size S and is of so n is of, let's say, depth d. Okay, then support of C. So by this I mean the size of the support set of C. The function computed by C is at least 2 to the n over log of S order d. Okay. So that this is what I mean. So you expect if S is small and d is constant, right? So then then this means that these functions would have large support set, right? So for instance, if S is polynomial size, this is again a polylog fraction of the full support, and so and is just an extremal case. So if this conjecture is true, then the dual of Hastad is true, right? Because then this means that and this implies, if this conjecture is true, this implies and, which is an extremal case of a small support non-trivial function, is not in CC0, right? Which is basically dual to parity is not in, or generally MODm is not in AC0.
That's your conjecture.
Yeah, that's my conjecture. Well, actually, the fact that and is not in CC0 is not my conjecture. It's yeah. This is yeah. Okay.
Can you expand the intuition about it? I mean, why do you think that this bound holds?
Well, because I simply cannot find any circuit which even gives a support of 2 to the. So actually, something even more perplexing is that I cannot find a circuit with using just MODm gates that has support 2 to the alpha n, for where alpha is less than 1.
Yeah, but I'm asking about the dependencies between the S and the D.
Well, because you will see for depth 2 this is true, because you have a log of S dependency, and this is just extrapolating from what we know about depth 2 to general depth, and there's no special reason other than that.
So if you had instead of MODm gate, take some gate that computes a balanced function, some function that's one probability half, and it's a universal, so you can compute anything. You would get lower bounds trivially for bounded depth.
Sorry, can you repeat?
If you take a function that's balanced,
Okay.
balanced, very close to balanced, and
Meaning half the time. Yeah, okay.
suppose it constant depth with itself. I mean, to stay.
Will it stay balanced? You're saying rough, near balance.
Yeah, so you get some trivial low bound for n.
Well, yeah. I mean, I cannot show that obviously, but
You don't even conjecture that. Yeah, the conjecture is specific
to MODm.
MODm.
Because I think this in general will not be true, because it will also depend on the distribution of the support. So MODm is sort of a very uniform function, right? I mean, it's uniform. The support is nicely uniformly spread, and you might have a very skewed distribution, and then this is not true.
Boss pointed out that if you take majority, then it's not true. It's balance function.
Right.
The thing about it's using majority by duplicating bits, you can directly compute the n. For example, you can take such a balanced function and make it unbalanced immediately.
Right.
It's not clear how to do such a trick to mod a finite number. I mean, you cannot.
I mean,
By composing.
yeah. Yeah, somehow that in general the conjecture should depend on the geometry of the support, but that I'm sort of overlooking here because MODm has this nice geometry.
Destroy the first weakness as well.
Sorry?
But if you add the first weakness, because I guess the second weakness is not enough, but the first weakness.
Well, the first weakness should not maybe say anything about the about this conjecture.
This is also true for majority.
This is also true for
This is
majority.
also the first weakness, as it is. No, I mean.
Well, it depends what you
Well, but it's not exponentially small. Like it's like I mean, the point is majority does not have exponentially small correlation with mod q, because in depth 2 you can compute mod q, right? But it has 1 over n small.
If you have really exponentially small correlation with something and you really allow only these gates, only the gates that have exponentially small correlation with the examination,
Yeah,
then at least maybe you can.
yeah, that's an interesting.
No, what do you mean?
It looks more, yeah, no, I'm
No, but he's saying that gates, if gates now have this first weakness as well, I mean they have exponentially small correlation.
But it doesn't mean that composing them even twice will have this problem.
Well, the AND function has exponentially small correlation with mod q, right? So that I mean, and that has very small support.
So here, Boaz's example. Say we allow two types of function, a random function and a random function parodied with thresholds.
Uh-huh.
Okay. Then individually, each of those gates is going to have support set a half, and it's going to have no correlation with anything. But if you sum them, then you get majority. So if you put them together, you get TC0. And of course, you can take any other function you want. So 1 and 2 are not enough to prove a general.
Well, of course, I insist that the two, you have only one gate.
Okay, but I'll have a bit that says which one of
Which,
Right.
okay.
Yeah. Yeah, I think the only reasonable, maybe slight generalization of this would say that you have a symmetric function which is periodic with constant period.
Right,
That's
right,
the only-
right,
but
right.
it's not much bigger.
Different from MODm, right? Yeah. Okay. And so let me also state something which probably everybody knows, but the point is we don't know even of an explicit function in, like, let's say, we don't even know whether NP is contained in CC0 of 6, as far as I know, linear size. This is not known. Okay, as long as the circuits are non-uniform. Okay, so all right.
You can't even negate in that model, in this model, right? Only.
No, you can negate because you have negated inputs available to you.
Yes.
So
If you want to negate the entire function,
you can do that. I mean, a not function can be computed by mod 6 gates.
You add 5 1.
Yeah.
oh, okay.
Yeah.
Do mod 6.
Yeah. So you can compute the not function.
Yeah, no, in terms of not costing too much, but yes, but
It's
you can.
universal to do a
Yeah.
negation of one bit.
You do it at
Maybe you need FC 100.
So really, the conjecture is that the support can't be very big or very small. It's
Right.
somewhere in the middle.
Yeah. But as I said, I mean, it's very interesting. I mean, it would be very illuminating, at least, to find a circuit that computes a function whose support is 2 to the alpha n, and alpha is less than 1.
If you do that, then can you compose, like, I guess,
Uh,
if you, for example, if alpha is less than half, then like a random, you expect to have no collision, so the end of 2 of these guys should be like almost no support.
If what is,
Just get that. Then maybe you can do more.
I mean, I don't
But
see
then
right
if
away.
you could get that, maybe you can get everything, because once you get down to like alpha less than half, then if the outputs will
Then maybe
but they are not random.
may not be random. Maybe you get only the empty or whatever.
Yeah.
Do you know the
Oh, so that's a very good point. So this conjecture is very strongly true in the case of primes. That's a very good point. Yeah, because very strongly meaning, it does not even depend on size. So for the following reason, well, I was going to get there because I need polynomial representations to be introduced there. But if you have a constant depth circuit just made of, let's say, mod p gates, then there's an exact polynomial over Zp of constant degree that represents there's a polynomial over Zp that exactly represents the output of this circuit and has constant degree. Okay? And it is known that polynomials over Zp of constant degree have very large support. They have exponential support. In fact, it's known that polynomials over Zm, so the following fact is known. I mean, if you're interested, this is a fact that if P has a constant degree, so P n is over the ring of Zm, right? So P is a multivariate multilinear polynomial, right? Then if and
because 0, 1.
yeah, I mean xi square is xi, right? Because we're looking at the space of functions from 0, 1 to the n into z of n, right? And the multilinear monomials form a basis set for this space, right? So if P has constant degree over z of m, and let's say A is in the range of P, then the size of P inverse of A in the cube is omega 2 to the n, right? So that's known even for non-primes. The point is, I mean, you can't if you have MODm circuits, of course, you can't express the output exactly by a constant degree polynomial. In fact, provably you can't. You can't do that, right? So therefore, this theorem is of no help when you have mod 6 gates, even with depth 2. In fact, even with depth 1, it fails because you can't express it. Okay, and but when m is prime, you can do that, and therefore this conjecture gets very strongly verified for.
Effect is basically, well, essentially the fact that the Reed-Miller code has linear minimum weight, right?
Yeah, but no, but the point is okay, over GF2 maybe this is true.
Over GF2, of course.
But when you go to
you replace x by x to the
no, but when you have m, and I'm now here talking of the support intersected with the cube.
m is a prime.
No, m is not a prime now. I'm saying this is true for any general m.
So
This fact is true for any general m. So there's a Ramsey theoretic argument that will show you this. Okay? Because the trouble is you're only intersecting the inverse image with the cube, right? So you can't use. I mean, you have to be more careful.
for primes, I see that you can use.
Yeah, for primes, yeah, for primes you can show it by simple argument. Yeah.
So the constant in the 2 to the n in omega is something like 1 over 2 to the d, 2 to the degree?
No, I mean, so this the argument that I know of uses Ramsey theory, and so it uses Ramsey theory on d-uniform hypergraphs. So there's a very bad.
For primes, it's something
Oh,
like 2
for
to the d.
yeah, for primes it is 2 to the d, right? Yeah.
So for composites, it's not known
no.
kind of what the type constant is.
No, as far as I know, no.
Dependence on the degree.
Yeah, so that's a nice question, in fact, of independent interest. A very natural question.
It's not too bad, right? Should be 2 to the 2 to the d.
For non-primes, I don't know how to.
For D uniform is 2 to the 2 d minus 1 times or something.
It's a tower.
Well, I mean, this is the point. Is this is not D uniform even, right?
No, but you apply it for D and then for D minus
It's 1 and so on, and so you get that number. Okay, whatever that Ramsey number is. Yeah. 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 But it's bad, right? Okay. Okay. So yeah. So it would be nice to. I mean, these things are nice questions, and obviously using Ramsey is not the right way because we're losing completely the arithmetic. and you're just using hypergraphs with no structure in it, and that's bad. Okay. So maybe I should stop now for.
Whenever you make the decisions.
Okay, I'm fine.
It's good for you to stop now, so let's stop.
Yeah, because I was going to get into polynomial.
Sure, okay.
Or maybe, okay. No, I changed my decision because let me state the two theorems that I'm going to show, the proof of the two theorems, okay, which are obviously very far from these two conjectures. Okay, so what I will try to show in the rest of the talk today and the next talk is these two theorems. So this is joint work with Christopher Hansen. So this was improved by Hansen later using other techniques, but I think this is still interesting. So circuits, let C be a circuit of let C be an AC0 circuit having S mod M gates and C must Okay, so it says suppose so we're going to attempt understanding MODem gates from two directions. One is we'll take an AC0 circuit and we'll augment it with as many MODem gates as we can handle, right, and prove lower bounds for, right. That's one way to approach Smolensky's conjecture, and the other one will be, well, we don't allow any AND and OR gates, we just have MODem gates, right. So the first theorem is progress in the first direction, where we say suppose C is an AC0 circuit which has S mod M gates, right? Then C must have size this much. So here R is the number of prime factors that M has, the number of distinct prime factors that M has. Okay, so then.
And the depth doesn't.
Well, I've assumed the depth to be constant, right? The depth appears here. I have to recall how exactly it appears.
Not in the exponent.
No, it's not. It is yeah, it is in the omega. It is in the omega.
Okay.
Yeah,
But
it's certainly in the omega. Yeah.
okay.
Yeah. So it has this much size to compute the mod Q function or the majority function, right? If M and Q are coprime, as before. So for instance, if you had M to be 6, then this just shows that if you allow little o of log of n many mod 6 gates, then you need super polynomial size to compute mod 5 or something like that, or majority. And this is sort of dual to something which is known, I think, because of due to Beagle, Aspness, et al., that if you allow because when you augment AC0 circuits with majority gates, then stronger lower bounds are actually known. It is known that if you have polylog many majority gates in an AC0 circuit, then the parity function is hard, or any mod counting function is hard. So it's sort of dual to this, but there they can handle polylog many majority gates, which is sort of interesting, because you would think that majority gates are somehow more powerful, but their argument can tolerate polylog many majority gates, but there's no known result which can say things about polylog many MODem gates.
What about other symmetric functions? Other than majority, it's not known.
Well, I mean, it has to be something like either majority or mod of m, right? I mean, you can say other things about other symmetric functions which are very much like mod of m. They're sort of periodic with a small with a small period that's a power of q, for instance, and m and q are co-prime. Then obviously you get the same result. Right? But the basic weakness is that you can't count mod of q. So that's one theorem, okay? And the other theorem that I want to prove is, and this proving this will involve combining sort of Hastad switching lemma and extensions to Razborov-Smolensky. Razborov-Smolensky worked with polynomials over ZP. We will now work with polynomials over ZM. This gives rise to difficulties, so you have to put in new ingredients into that. So by combining these two ideas, we can prove this result. And the other result is that if C comprises only MODem gates, and as size S, then the support of C is at least 2 to the n over some function, some constant that depends just on m to the s. Right? So, and this is independent of depth, actually. So this does not depend on depth. But it is obviously very bad. S is the number of gates. No, it's number of gates. Yeah. Okay. So obviously this is much weaker than this conjecture, but it at least says that if you have sublinear size, no matter what depth you have, you cannot compute the AND function. Okay. Which is interesting because, as Pavel was telling me the other day, I think if you look at formulas of depth log of n, or and if you include parity gates in your formulas, then you have no interesting lower bounds. No, I mean you cannot prove an omega n square bound for any function, right? So here, I mean, if you have circuits. Well, then independent of the depth, we get at least linear lower bounds.
Probably, if you don't restrict the depth, you cannot hope for something better than this, because
Right. So this is tight in the sense that, I mean, if you don't pay attention to depth, this is tight because in linear size you can compute the mod q function or AND function or any of this function that give rise to a regular language, in fact, in log of n depth. So this is tight in that sense. But the weakness here is that you will see that this is sort of an information theoretic result. And so it's not taking into account. Basically what it's saying is even if the base layer is not of linear size, then you lose information already. Okay, and then the circuit would be forced because the base layer itself would get fooled. Right, so it's in that sense an information theoretic result. And so it's not taking into account what the computational power of the sub-circuit that's being fed by the base layer, right? So that's, it does not matter actually. Even if it's a non-layered circuit, the result still holds. Because what you can think of is in the following way: even if the circuit is not layered, you can only think of the gates which are below the base layer. They might still draw inputs from maybe fed by the input gates, right? But if they are sublinear in size, you can just ignore the inputs that are being fed by the by the base layer.
Well, you will prove it.
Yeah, I'll prove it. So it's better to show it for me. Okay, so I'll take a break now.